and then I will have you write the quiz, you turn it in, and of course that is not for grades. So it's essentially to see, for you to check yourself out. So you make the, you solve the problems and turn it into me so that I can go through that over the weekend. And if any of you have some issues, I can discuss that on Monday so that you're better prepared for the exam this time around. You know, the first problem which I already did the other day was the R0 line. I said is NHCl. And then I asked you to calculate the position of the R0 line for and I also said what we are essentially looking at when I say it's an R0 line is that it is V0, J0. So where is the R going to be? It's going to be delta J equals. So it's going to be plus 1. So if you really work on it, I'm making a transition. Okay. So you have to figure out, there are two components to the isotopic shift. Of course in the exam you don't have to prove both of them to me. But I want you to go through that problem here. And in the exam, if I ever ask you this question or some modification of this question, which involves both the vibration as well as the rotation, it's enough if you take this series and tell me that in the case of the rotational shift, it is going to be much less compared to the vibration shift, and therefore I am calculating only the vibration shift. But you have to tell me that. If you don't tell me that and you simply do the vibration or the rotation to give me the answers, so that's not a complete answer. So basically when you do this, what happens? You keep this as your reference level. This is going to shift somewhat because that's your vibrational part, and this will shift relative to this because that is going to be the rotational part. So you've got to calculate the shifts that are going to be there in both. What's the shift in the vibration going to be? We said the vibration for HCl, let's say I do it for 37 first. And that we know is the frequency is 1 over 2 pi root of k by mu. But when you change to a different isotope, you also know that the force constant stays the same because the potentials don't change when you change the isotope, because the potentials depend on the number of electrons the system has and so on and so forth. You're not tampering with the number of electrons when you actually do the isotopic calculation. So the force constant stays the same. The force constant actually has to do with the curvature of the potential curve. That stays the same. But what will change, of course, is your reduced mass. And when that changes, of course, 2 pi is the multiplicative factor, which also will get cancelled off. And therefore you will have mu HCl 35 divided by mu HCl. Of course, when you did your rotational calculation, you had to calculate mu. What did you do? You took the mass, you divided by the Avogadro number, you converted them to kilograms and all that, because you had to get B in the right units. Here you are taking two ratios. So there is really no need for you to do all that. You don't waste your time in the exam getting them divided by Avogadro numbers, and the more numbers you put, the more chance of an error in your calculation in any case. So you don't want to do that. And when you do this, what happens? It is simply 35 into 1 divided by 35 plus 1. That's enough. And this one is going to be 37 into 1 divided by 37 by 37 into 1 divided by 37 plus 1. And when you do that, this you will find is going to be 35 by 26 into 38 by 37. This is the half of this, and this is this. This turns out to be root of 0.998. Please take on these numbers because this way it serves as the solution to the whole problem, including the final answer. Go back and check to see whether my numbers are right. Even though I keep telling you that your numerics must be good, mine is a very great eye. I can make mistakes, but I can afford to make mistakes. I don't have any exam, you have. So this basically becomes coming to the for HCl 35 into 0.992. So therefore, if you go back and calculate, if you assume that 2905 is the frequency for HCl 35, then the HCl 37 is actually going to be omega plus HCl 37 is going to be 2905.8 into 0.9992, and that will be 2903.6. And what is the difference between the two frequencies, between the HCl 35 frequency and the HCl 37 frequency? Is simply the difference between these two, and that is going to be simply 2.2 wavelengths. So what does this tell me? It tells me how much this level is coming down for the HCl 37 relative to HCl 35. While the HCl 35 has a frequency roughly around 3905 point something, the HCl 37 is 2903 point something. So there is a shift of about 2 wave numbers, 2.2 wave numbers that is coming from the vibrational part of the whole problem. But then we don't know, the rotational part also suffers from an isotropic shift. And how does that come about? What is this shift really? How much is this energy difference? 2B, you know that, it's 2B. So what do I really need? I need to know the B value for HCl 35 versus the B value for HCl 37. If I know the B value for these two, then essentially I know 2B in one case and 2B in the other case. And that difference between those two 2Bs will be the shift in the frequency as far as the rotational problem is concerned. So all you have to do is to go back and do it, but then what is B HCl 37 divided by B HCl 35 going to be? Simply mu on small square root is going to be mu HCl 35 by mu HCl 37. That's it. And what is that? You already know that. It's 0.998. So the two B's therefore differ by this much. So what is the difference in the two B's? Why one of them is 1, the other one is 0.002, and therefore the frequency for one, if it is 2B, and let us assume B is, how much can B be? Approximately. You know what the order of magnitude is going to be. 5 wave numbers, 2 wave numbers. Assume 5, you're not going to be terribly wrong. If you assume 5, in one case, what will the B be? It will be, 2B will be 10. In the other case, what will the 2B be? It's 9.98, that means the B value for the heavier isotope. If the lighter isotope is 10, for the heavier isotope it's going to be 9.98. So what is the difference between the two isotopes? Like 0.2, 0.02 wave numbers or thereabout, which is much smaller than what you see for the vibrational problem. And that is the reason you really don't have to worry about taking into account the rotational problem when this is asked of you. Unless, of course, you are a high resolution spectroscopist who worries about every 1/10 of a wave number in your experiment or 1/100th of a wave number in your experiment. In which case, of course, you will write out the entire equation, including vibration and rotation, and worry about the isotopic shifts for each one of them. Because maybe your data is so precise, maybe your data has the accuracy within 1/100th of a wave number, and you want to account for every shift that you see in your experiment. We won't worry about it at this point in time. But at this point in time, you're really looking at a fundamental course in spectroscopy. So we will not worry about high resolution data. All I'm trying to say is that if you are confronted with a problem of trying to look for isotopic shifts between vibration and rotation, worry about vibration. Because the rotational shifts will be at least an order of magnitude, a factor of 10 or maybe a factor of 100 smaller. So while this is 2.2 wave number, the other one will be like 0.2, 0.02 depending on how much your B value really is. Therefore, you really only worry about your vibration part. So which means if the R0 line for HCl 35 came at 2905.8 and I ask you what is the R0 line for the HCl 37, you know what it is. It's just 2903.6. You don't have to factor into it the shift due to the rotation part. In fact, when you put the HCl or DCl or H, heavy hydrogen, and the Cl35 molecule, you will find that the shift due to the deuterium is quite large. In fact, if this comes up to 2903, there is something like 800 wave number shifted away. Because when you are changing HCl to DCl, what are you doing? You are changing the mass from 1 to 2, so 50%. Almost twice. That's what it is. Different by factor of 2. Whereas changing 35 by 37 is 2 parts per 35. Much smaller. Changing H2D is 1 part out of the way you look at it, 1 part out of 1 or 1 part out of 2, but it's still a large number compared with the HCl37 problem. So this is your answer. 2903 is a shift of 2.2 wave numbers, and when I ask you this question in an exam, you must put it in there that the vibration problem actually provides for you a larger isotopic shift than the rotational problem, and therefore I am calculating the vibration part and giving you the shift due to the vibration. That would be a complete answer, and that is what I will be looking for. If you just give me the vibration part with none of these statements, well, I will still give you a marks, but I want to tone it down a little. So if it's a 3-mark question, maybe you get 2.5 or something, because you haven't told me why is it that you just calculated 1/2 of the problem and not the other half. So you've got to learn to be precise in what you're saying and tell me why you're doing it the way that you're doing it. Any questions on this problem? Okay. Yeah. Pardon me? 2D.
Why you are not getting 2D?
Well, I could. That's what I'm trying to say. I could add that shift also. But what will happen? It will be 29.03.6 plus that very small change that I was talking about. It will be so small that I really don't have to worry about doing it. That's why I said if you had a high resolution data which gave you frequencies precise to maybe a 1/100th of a wave number, then I would want to incorporate that also. But in a paper like this, when I ask you the shift, don't waste your time doing the rotational part. Well, if you do it and you give it to me, I'm not going to penalize for you, I'll probably appreciate it. But the point is, if you know that the vibration shifts are going to be much greater than the rotational shifts, that's what I want you to pick up as a lesson from this problem.
Suppose H2Cl35 is 3 greater.
For H2Cl35, I think I have worked out. It is 822 wave numbers for the vibrational problem. And how much is it for the rotational problem? It's 2 wave numbers. So the vibration part actually shifts by 800 and the rotational part shifts by 2 wave numbers. So you're still being dominated by changes in the vibration part, and that's what I'm trying to take. If I need you to do both, I will ask you for that. My question is very explicit. The sense that please do calculate the shifts due to vibration and rotation and give me the complete shifts. I'll probably do that in the final exam. And the reason why I will do it in the final exam is because you got 3 hours. You got to stay busy for 3 hours. I got to keep you busy for 3 hours. Therefore, I will have these problems worked out that way. In a 1 hour exam, I can't make you do all that. Because by the time you finish with this problem and you calculate both of these, you would have probably already spent about 20 minutes. And it's very hard to be able to ask you. So in a mid-sem exam, I like asking reasonably larger number of smaller questions. Because if I just give you 2 questions, I think it's a little unfair for you. Because if you knew those 2, you are okay. If you didn't know one of them, you are finished. 50%. But if I ask you about 5 questions, 6 questions, if you didn't know 1, you're still okay because you knew 5 out of 6. And that's the reason why I do it, so that I give you ample opportunity to be able to tell me that you have understood the course to a greater or lesser extent. But 2 questions, each one taking you about 20 minutes to solve and 25 minutes to solve. That's a lottery. Because those 2 questions, if you know it, you know it, you know it. If you don't know it, you can leave after 10 minutes because there's no point in sitting there and not knowing what to do. So I don't want to do that. That's the reason I asked you a few more questions, like 6 questions, and so that somewhere if you didn't know. But of course, if you're well prepared, you'll be able to answer all 6 anyway. So that's not a big deal. Yeah.
So is that the way number given is for
this R0 line, when I say it's R0, it is for a low vibration thing, because the moment I say R, I have brought the rotational part into it.
But we ignore the 2dm part in the...
Well, we don't really ignore it. When I say the R0 line is 2905.8, in fact, when I do the, first we just do one thing, we just wait. Let me do the fifth problem. And the fifth problem will answer a question. If it still doesn't answer a question, we'll come back and discuss it. I think the fifth one will answer in some ways as to what you're trying to answer. Okay, if that is taken care of, let's move on to the next one. But you need to show me all these steps in the solution of the problem. And it's good for you to put all these steps, because if you put all the steps everywhere, right through, you also tend to make less errors because they're all staring at you, but you can't really make mistakes. But the problem would be, you write this, and steadily you want to get here, and this is done somewhere in the last sheet as some, rough work, have already made a mess of it, and then this will become, who knows, 10 or 14 or something, and then you get some numbers which are so beginning. So it's always good that you carry these numbers as we go along, because then you don't make mistakes. See, if you're prone to errors, like some of us are, like I am, you have to find ways to tackle that. Because some people are very accurate, they won't make mistakes, numerical mistakes. But if you know that you are somebody who is going to make numerical mistakes, then you have to find ways to somehow catch it. And that's one way to do it. After using the low vibrational spectrum of HCl, calculate B0 and B1. Actually, the question you asked will get solved with this form, not question 5. Using the low vibrational spectrum of HCl, which is given below, and which I keep telling you, hopefully one day you will record it yourself. Calculate B0 and B1. And what do I mean by B0? B0 is the B value in the B equal to 0 state, and B1 is the value of B, the B equal to 1 state. In the first approximation, you say that these two are the same, and then you go about having a nice time. The equations are simple. And then you come back and say, well, they're not really the same, and they are actually different because the average internuclear distance in the two states are different. Therefore, they must be different. And then you come back and try to calculate what the B0 and B1 must be, and they are different. So let me see how we can do it. The spectrum is given at the bottom. So I might give you something like this. I might give you this spectrum, or maybe I can give you a carbon monoxide spectrum, or some other spectrum, or I might just make up one spectrum. Simply put some numbers in there which really mean nothing in terms of an experimental spectrum, but it's still a problem for you. I hope it's not a perennial problem. You'll be able to solve it eventually. And that's what we're trying to do. And what I'm trying to do is to ask you, using the spectrum, get me answer B0 and B1. So all there is to it. And what you do in such cases is the following. B0, J0. B1, J0. And that's 1, 2, 3 in terms of J, 1, 2, 3 in terms of J. And of course, this is totally out of scale. This must be up there. I am not tall enough to keep the scale on, therefore I will do it this way. Okay, now what do I really do to solve this problem? I need the B value for this, I need the B value for this. And I will outline the way I expect you to do if this ever shows up in the exam. Supposing I take this line, I take this transition. What transition is that going to be? It's an R branch because the upper state has got a higher quantum number than the lower state, and this must be R0 because the lower state is R0. And then if I start from here, and I can't do, let me go from 1. Okay, if I go from 1, I go to 2, what line is that? R1. Go back to your spectrum. And what do you see in the spectrum? The spectrum you see on, and on this side is a gap here. What is the first one? This is the null gap. That's a gap that actually separates out your PNR. And look very carefully on the scale. Make sure which way the scale is going. The scale is the way I have shown it here. This is the larger wave numbers and that is shorter wave numbers. Sometimes I can be mean. I will twist the scale and put it small here and large here. You have to watch out for that. Because this is the case, which is the R branch in this case. This is the R branch. And that's your P branch. But if I simply overturn the scale and keep it the other way right, so the frequency increases that way, then that would be the R branch, which would be the P branch. So the moment you get your spectrum, the first thing that you need to figure out is stare at it and ensure that the scale is going which way. And then decide which should be the R branch and which should be the P branch. Now these are things we have to do. And that's the way a spectrum is always analyzed. And even in real life this happens all the time, because people will put up a spectrum in which it will be 4,000 on this side and 400 on that side. Somebody else will come along and put 4,000 on that side and 400 on this side. And if you don't recognize that he has done this, and every time you think the 4,000 is on this side, he might be showing you a low frequency mode which you think is due to an overstretch and completely have the whole thing misassigned. So you must learn one fact of looking at spectra. Make sure that your scale has been internalized. You know what the scales are, which way it goes. That's R. If that's R, what's the first transition going to be? R0. And what's the R0 really? 0 to 1. So you always put that. And then if that's 0 to 1, what is this? 1 to 2, this is 2 to 3. On this side, that's the P branch, and therefore this must be 1 to 0. And then there's going to be 2 to 1, 3 to 2 and 4. But be careful about having a little sloppy here, in the sense the way I have notated it, but the reason I have done that is, I will tell you why later. But this is 0 to 1, lower state going to upper state. Better still, put an arrow there, so you know who's going where. And here it is 1 going to 0, 2 going to 1. So now, if this transition is 1 to 2, that's an R1 transition. And where is the R1 transition over here? It is this fellow here. And what is the frequency of this guy? It must be the second line in the spectrum. And what is the second line in the spectrum going to be? 2925.7. So that's a 2925.7. It's the second line in the spectrum, and it's actually a transition that goes from 1 to 2. I can look at another transition, and that is a transition going from 1 to 0. And what is that going to be? It's going to be the P line, and it's a P line P1. And 1 is going to 0. And where is that line? It's right here. And it's the first line. And what's the frequency of that fellow going to be? 2865.2. Now let's see what's the logic in these two lines I have chosen. There must be a logic in it. Just not anything. What I have essentially done, I have chosen a common lower level. I have chosen a common lower level. And naturally from that lower level, the R should go 1 higher and the P should go 1 lower. Start from 1, I've gone to 0, I've gone to 2, and therefore the difference between these two frequencies must be equal to what? This is 6B, this is 2B, and that's 12B. 12B, 1, 1, 1. And let me put this right here. This is 0, this is 2B, not, this is 6B not, and that's 12B not. But since I've started from the same common lower level, I'm going to two different higher levels. the difference between these two frequencies the 60.5 nanometers must be equal to how much? 6V1. And therefore V1 must be 10 point up to 10.1. Now that's my B value, right? That's my B1 value. I've got the B value in the upper state. But what you do is you don't stop with that. You don't take one set of readings, always. You don't stop with one set of readings. You must always cross-check your numbers by doing something else. So I will start from the same 2 level and go to 2 other levels all day. So from 2 I will go to 3 and I will go to 1. And from that I can get my B1 value. And when I get my B1 value from that, it must be approximately the same as this. It won't be exactly the same. Because as you go higher and higher, we know that centrifugal distortion comes in and all sorts of problems. But if I've just gone from 2 to 3, I don't expect such a huge effects of centrifugal distortion, and therefore the B1 value that I'm going to get by simply choosing another common level, which is level 2, must be approximately the same. Please do it. The reason why you must do it is, if you have made a mistake in the first one, the second one will tell you that. Let's say you made some mistake and you got B1 as 10 or 10 or something, and this one gives you 10, then you know you made a mistake somewhere. And therefore you can go back and check. This is what I meant by saying that you must have your own way of checking yourself as you go through the problem. And even in real life experiments, nobody does one experiment and starts to report that. You always do a bunch of experiments, you cross check. You do it at different conditions, you do it under different temperatures, whatever. And make sure that you get spectra that are consistent. And then you start giving a theory to it, and you start assigning it, and you start looking at the science behind it. The most important thing in experimental science is the following. You can make mistakes in your interpretation. You can get a good spectrum, you can get a good experiment, and you can make errors of interpretation. Give a completely wrong interpretation. That's okay. Because if you publish it and then 2 years later somebody says this is absolute garbage, this interpretation is not right, well, it will make me sad, but it won't kill me. But if somebody comes and tells me your experiment was wrong, and what you have given me is a bunch of garbage, your experiments are wrong, that's probably the day one must quit science and just go home. Because if your experiments are wrong, you have no place to be. Again, that comes back to a question of honesty, because you have to be very clear about what you are presenting to the world as data. No problem if your interpretation is wrong. It only says that maybe under the conditions in which the experiment was done based on what you knew and what existed as knowledge at that point in time, it's okay. But your data can't be wrong. I don't know how many of you were there in the talk by Professor Balram the other day. And he was talking about Linus Pauling's DNA structure. And what did he say? He said it's still there in literature in book, but that he didn't mention one very interesting thing, two very interesting things. Linus Pauling actually had the DNA structure with the phosphates on the inside and the bases on the outside. And what's wrong with it? Anybody can tell you. Phosphates are charged. If you have a negatively charged species sitting on the inside, they must repel and rip the two DNA strands apart. That must be absolutely a meaningless structure. And for Linus Pauling to have made that mistake, remarkable. Somebody apparently said, once they saw